I'm going to talk about a little tool I wrote called Viasock. The tagline is Automagically Serverize your pipelines. So I'm going to talk to you about pipelines and about Serverize and about Automagically. So first, pipelines. Why am I interested in them? How do you reload on a Mac? Control R? Sorry? Command R. All right. So I work as a researcher in natural language processing, and for the last couple of years I've worked in this project, the Parallel Meaning Bank. It's a research project on translation, on linguistics, on semantic representation of natural language sentences. This is the web front end that is at the heart of the project. And in a nutshell, what it does, you put raw text in. So here, the example sentence, how does Tom do that? And after lots of processing steps, you get an analysis like this out. So analysis of word senses, of syntax, and of various other things that help the computer understand what the meaning of the sentence is. And in order to perform these automatic analyses, we need lots of often state-of-the-art tools produced by various researchers. For example, tokenizers that split up the text into its tokens, a parser that finds the syntactic structure of the sentence, a semantic construction system that turns all this into logical formulas, and various taggers that annotate words on the word level, as well as various glue scripts that perform conversions from the output of one tool into the input of another tool, and that apply manual corrections performed by human annotators as well. So how do you build a backend for that orchestrates this processing using many, many scripts? To do that, in this project, we applied the Unix philosophy summarized as follows: write programs that do one thing and do it well, write programs to work together, and write programs to handle text streams, because that is a universal interface. So yeah, we have programs that do one thing and do it well. For example, a tokenizer to split up the text, a parser to find the syntactic structure, a semantic tagger that finds the semantic class for each word, and so on. And they all work together. So it's one pipeline that also branches out. And yeah, they all work together. And all of the formats in between are sort of text formats. So we have raw text, we have various column-based formats, we have XML, we have Prolog. So different inputs, hence the conversion scripts. So we do it like this. And this is a very simplified view of what our pipeline might look like. So for the sake of the example, I only present two components, the tokenizer and the parser. So at the beginning, you cat the raw text, one document, into the tokenizer. We use a statistical tokenizer, so it loads a model from some file. And then we pipe the output of the tokenizer into the parser that also loads a statistical model. And finally, we write the output into a file, out/01.parse, where the front end can find it and display it. And we actually do something more sophisticated than just using a pipeline. We use a Makefile, or actually we use a produce file. So produce is an improvement over make in some sense that I presented at pyGrunn in 2014. But that is beside the point for this talk. Let's just look at the Makefile. The idea here is that we can run our pipelines incrementally. So we materialize the intermediate outputs in the form of files, store them, and then when something changes in our pipeline, which often happens because human annotators make new corrections, or our models are retrained and improved, or our tools are updated with new features, then we only need to run the part of the pipeline that has gone out of date. So for example, if we update our parsing model, then we don't need to necessarily rerun the tokenizer because the tokenized output is still the same. So if you're not familiar with the structure of Makefiles, this one consists of 2 rules. Each rule specifies how to make a specific type of intermediate input. So for example, the .toc file, the tokenized file, this rule specifies how to make that. So that is this part. Then right of the colon, you have the dependencies. So the first one is the raw text file that you need as input. And then we also specify the tokenizer, the binary, and the model that it needs to load as dependencies. Because of these change, we need to rerun this because it's gotten out of date. And then here the indented line is the recipe where we cat the input. This is a placeholder standing for the first dependency, so this one. We cat it into the tokenizer, and we use the model here, and then we write it to $@, which is a placeholder for the target of this rule. And then here the rule for the parser, which depends on the output of the tokenizer, has a very similar structure. And at a slightly higher level, what our system does is you have a daemon on top that orchestrates the whole thing, and it calls make, it spawns make processes, each make process for one document. And the daemon takes care of rerunning make when it becomes necessary, for example, because a user edited something in a document, made a correction to the annotation, then the daemon takes care of spawning those make processes that update the files. Okay, so this seems very neat. So kind of the concerns separated. Tools are doing their thing, and Makefile orchestrates the pipeline at a document level, and then the daemon orchestrates when to run make for which document. But we have a problem. Namely, those individual tools that we use. For example, the parser isn't really made for being run on a small document at a time. It's made for processing a large amount of data at a time. So here we have a whole corpus tokenized that we pipe into the parser, and then it loads its model in the first 10 seconds, and then it spends maybe 3 hours processing the whole corpus, which is quite all right. And the 10 seconds at the beginning are no problem. But in our use case, when we run it for one document at a time, so 1, 2, and 3 little files, then those 10 seconds of startup overhead of loading the model each time the parser is called are really unacceptable, because it maybe needs only 1/10 of a second to process one sentence. And if we have to wait for 10 seconds every time, it's not only a huge waste of resources and too much memory that is used here, it's also really not nice for the human users of the front end who, when they make a change, want the pipeline to run as fast as possible to see the results. So the classical solution to problems like this would maybe be to serverize the thing, and that is how we get to serverize it. So one classical approach that we, or let's look at the problem from a slightly more abstract perspective again. So we have multiple instances of a tool. Let's call it my tool. You give it an input, and you get an output. And the problem you have that you don't really want to have that many instances, because each one loads a model and wastes time by that. So the classical serverization approach would be to split up my tool into a client program and a server program, and then start the server once in the background and make it able to listen on a port or on a TCP port or a Unix domain socket, and then allow a specialized client program, my tool client, to access that server. And then the user interacts with the client in a similar way to interacting with the original program. And now you don't have the startup overhead anymore, because the server takes care of the actual processing. We employed this for one of the tools that we use for one of the parsers, because it already supported this client-server thing. Can anybody, though, see what's wrong with this picture? What isn't quite right? What's ugly here? Any idea? Any guess? Louder. That's one thing, but that's not what I mean. What more like the idea that we have violated the Unix philosophy here, the first rule. Write programs to do one thing and do it well. Now, if you imagine we have this my tool, maybe it's a parser, that did one thing well, namely parsing sentences, and now it does two things. Like we added this whole client-server code where you have to know how to listen on a port, you have to know how to connect to one with a client code. You have to add all that into your existing program. And if you have several programs, you have to do that for each program. That was the problem we had. These were written in different programming languages, so very little chance for code reuse as well. So what you want is to separate this concern of client-server calling out into a separate tool. And that is the first idea that how Viasock was born. So I realized that I had to do this for performance reasons, and I didn't want to do it 4 times for each of our tools. So I started writing this tool that does this. And the idea here is that you leave your tool unchanged, and then you have a specialized program Viasock that does the client-server stuff. So you spin up the server automatically spins up an instance of my tool in the background, and then you have a Viasock client that connects to the Viasock server. User sends their input to Viasock client that forwards it to Viasock server. The server serializes all the inputs that it gets from the various clients, sends them to my tool one record at a time, and waits for the corresponding output records, and then sends the outputs back to the client that corresponds. There are some assumptions here in order to make this work about how my tool works, right? So we want my tool to do its startup overhead, the model loading at the beginning once, and then process an arbitrary number of records and independently of each other. So, for example, if one record is one line, then my tool should process one line at a time and then forget about it and then be in the old state again before processing the next line. And that is quite a common pattern in Unix programs, line-by-line processing, or also different types of records processing. For example, one record might be a chunk of lines terminated by an empty line. So various formats are supported, and my tool needs to send back the output before waiting for the next input. So it also needs to flush its output buffer before reading the next input. And that is something, unfortunately, not all tools do, so we couldn't always just drop in those programs. But with a little adaptation, it worked quite well. So how do we actually use this? This was our old Makefile with one rule for tokenization and one rule for parsing. So here we call the tokenizer, here we call the parser. And how do we now make this work with Viasock? Avoid this model loading every time we call such a rule. This is our first attempt. So instead of calling tokenizer, now here in the recipe, we call Viasock. We pass the subcommand client, which tells us to start up in client mode. And then this argument here is the socket, which it should connect to. So we assume here that a Viasock server is already running in the background with a tokenizer, wrapping a tokenizer, and then we can just cat the input into Viasock client, and it will connect to the server and then wait for the output, and that it will give back on standard output. So we kind of have a drop-in replacement for calling the tokenizer directly. Okay, this is our first attempt, but it's not really good yet. So what is wrong in this picture? Exactly, yes. So this part here doesn't make sense anymore. So we declared the tokenizer and the model as dependencies. But this doesn't help us anymore, right? So make is good at this thing of keeping track of dependencies and noticing when they changed and then saying, okay, if the model changes, then I need to rerun this recipe, then the output is out of date. And it will do that. It will notice when the model has changed, but it will still now call the client, which connects to the same server, presumably, which has not been restarted unless we did that manually. So there is some magic missing here. So that is why we want to automagically serverize pipelines. And so this is the setup we had, where we have this client server stuff in between. So we got rid of the problem of the startup overhead because we have the tool just once running and connect to it via a lightweight client. But we now have this whole problem of managing the server on our hands. We need to make sure it is running, and we need to make sure it is restarted when something about the tool that it is wrapping changes. But really what we want is for this middle part here, for the server client part, to be a black box. We want this to be as transparent as possible, and we want to keep using Make for dependency management and just rely on things to be up to date. Is that too much to ask? Well, that is why I introduced the magic command, so another subcommand for Viasock. Viasock server and Viasock clients are subcommands. They are plumbing, so you shouldn't really be using them in day-to-day use. What you want to be using is Viasock run, and that makes the whole process very transparent, because the arguments to run is just a command, the command that you would have run ordinarily without the Viasock layer. You pass that to Viasock run, and it automatically checks if a server corresponding to that command is already running. And if so, it just uses that, it connects to that and uses that server. And if not, it automatically starts one up in the background without further ado and uses that. And of course, you can use it with multiple commands. So here we have my tool, my model. You can also use my other tool. In that case, it will of course start up a different server that wraps a different tool, and it also looks at the arguments. So if you pass it my tool my other model, then we'll start yet another server that starts my tool with my other model. And it doesn't only look at the program name and the arguments itself. It also, if those arguments refer to files, such as my other model refers to a file, it'll also look at the file itself and its modification time. So if the file was modified since the server was started, then it will also know that it needs to start a new server. If that happens and there's still the old server running, what happens to the old server? Well, the current policy is that we leave the server to itself. We don't actively kill it, even though it's out of date. Instead, the server itself has a timeout, so it notices after a while, I haven't had any client connections in the last hour or so I'll just shut down, and this timeout is adaptable. So that is the magic of Viasock run. And with that, our Makefile looks like this now. And it looks exactly like the original Makefile, except for this Viasock run, which we just prefix to the command we really want, and Viasock run takes care of all the bringing up the server and choosing the right server stuff and so. How am I doing on time? Good. So here's a fun technical detail. How does this actually work under the hood, connecting to the right server? Every time you call Viasock run, how does it determine which server to connect to? Well, there's a server ID, and the server ID is just a hash of all the relevant information that you need to identify the right server. So that's the options to Viasock itself, such as like this one, which controls the server timeout after 3,600 seconds shut down if no requests are made. The program name, of course, the modification time of the program, and the same for any arguments. So here you have the model. This goes into the hash, and the modification time of this file, if it exists, goes into it. And then Viasock run will use a server or start a server which listens in the current directory in .viasock sockets, and then the file name, the socket name, is the server ID. That's how that is done. Right. To summarize, what was the problem I was aiming to solve? if you frequently run a program that has a high startup overhead and you run it on small data that don't really justify this high overhead, that is the problem it's made to tackle. The conventional way of having client-server setups has a number of problems. First one, poor separation of concerns. If you split up one tool into client and server, then this whole business of doing the client-server communication is really a separate concern that putting that into just any program is really messy. And it's often not practical to reuse the client-server code, especially if you have multiple programming languages. What's arguably even worse is that you have suddenly DevOps on your hands. So you have to make sure that the server is running when you want to use it, and you always have to make sure that your tool is connecting to the right server, which is running an up-to-date version of tool and its inputs. And this is just, well, of course, mistakes are bound to happen in such a situation. So you can't really sleep well at night because you don't know if your pipeline is really up to date. Also, if you want to be flexible and run your tool with different options at different times, right? So maybe try out a different model just once, then usually you would have to start up a new server just for that. You could, of course, write your client-server protocol to include all kinds of options and then make the server handle that. But yeah, that's a lot of overhead, and you're duplicating your command line interface, and who has time and money for that? The Viasock solution is to leave my tool exactly as it is, modulo the things I said, that the assumptions we have about its input-output behavior, to have a Viasock server process that wraps it, and then you have the Viasock run command that provides transparent access by handling the following aspects: starting the server if needed, making sure that you use different servers for different sets of options and programs, and make sure that a new server is started when the program or any of its arguments, its file arguments, change. Some limitations. The first one that could be easily implemented, I think, if your tool's throughput ever becomes your limiting factor. Like if it cannot handle as many input-output records as your clients would like if you have so many clients and there's so much throughput there, then it would make sense for the server to spin up multiple instances of my tool and balance the load between them. That could be added. A more fundamental limitation is the second one, that you have certain restrictions on how my tool processes input and output. However, in most cases, if you have access to the source code, then it's relatively easy, I think, to make sure of that. So process one record at a time and flush the output buffer after each record. All right, here's a picture of many colorful socks and the link to the GitHub repository where you can find this, and maybe it will be useful. I hope so. Thank you.
Thank you. We have a few minutes for a few questions, so if there's anybody.
Hi, thank you for your talk. But how can you see whether an argument is, let's say, a flag or a file name? How do you distinguish the two?
So I'm not doing anything clever there. It just checks if the argument is a path to an existing file. And if so, it uses the modification time of that file to the hash, and otherwise it just puts 0 instead. So if you happen to have a file that is called -m, let's come up with a scenario where this would actually be a problem. If you have a file called -m and that file changes its modification time, then you might be doing unnecessary work because it will then start a new server. Fairly unrealistic scenario, I think.
Other questions? Anybody else? Way in the back, like that.
Hi. So if I understood correctly, all your sockets live on a local file system, so
Yes.
this does not work over the network, it's all confined to one machine?
Yes, right.
Do you have any plans to make it work over the network that might also solve your load balancing issue?
No, it didn't occur to me. I know that there are similar tools around that where I perceived it as to be one of the problems that they use TCP sockets and which can be a security risk. So I saw this using Unix domain sockets as a security feature. But of course, yeah, it might, of course, be handy to be able to do this over the network. But then I would also like, then the special the special feature of Viasockets, of course, that it handles all the bringing up the server and so on. So you would have to add quite a bit more than being able to connect over the network. You'd also have to start the process on the different server. So I don't have any plans for that, but...
you can use socket activation for that using systemd or inetd or something like that. And the files could live on a shared storage, so then you have all your files accessible on one central store, and that might expand. I was thinking, like, if you have files which are huge and you need to process them all in one evening, then being confined to one machine would be quite limiting.
Yeah, right. Yeah, so the problem hasn't come up for me, but if it comes up for anyone, I'm happy about pull requests.
Okay, thank you.
One final question, maybe? No? In that case, I'd like to thank Kilian for his talk.
Thank you.